Hi everyone. Today I'm going to cover the poster for quantum secure non-malleable codes in the split state model. So let me begin by introducing what non-malleable codes are, followed by what each term means in the title, like what is split state model and what do we mean by quantum secure. So let me first go through what non-malleable codes are. So non-malleable codes are a kind of relaxation of error detection codes. So let me first recollect the error detection code setting. You have an initial message M, and then you have an initial message M. Error correcting codes encode the message M to code word C, followed by channel which tampers the code word C to C star, and then the decoder decodes it to M star. And what we need is that from out of error detection codes is that M star is equal to the decoded message is equal to per. It's a about condition that with high probability or about condition. This is what we need from error detection codes. So when is it possible? We know that it is possible when Hamming distance between the corrupted code word and the actual code word are linear in the length of the size of the code word. Here, as you can see, I've mentioned the code word size is like n, and where head stands for Hamming distance. So we know that when Hamming distance between code word and the corrupted code word is linear in the size of the code word, then such error detection codes are possible. So this restricting that Hamming distance between the code word and corrupted code word is constant is a specific set of function families. So now one can ask, what if your channel corrupts with much more general function families? So this is a question that non-malleable codes try to answer. And again, let's come back to the setting. You have the initial message M, code word C, and then you have a adversary who is acting by a function trying to corrupt the code word. And then after you decode, you have message M star. So we need to place some bounds. So the thing is that adversary is bound by this function family F. So adversary is, this is how we capture adversary in the model. And then what non-malleable codes say is the following, that for every message M, the decoded message M star is a convex combination of the initial message and a distribution that doesn't depend on the initial message M. Here one might ask, what is this M star is? So as here I haven't specified, but the encryption is randomized. So that's where we get the randomization here. So now we know that it is possible as long as the adversary is bounded by this function family of this size. So now let me now explain what split state model is. In split state model, we have initial message M. The code word is in two parts, C1 and C2. And then adversary is allowed to tamper C1 and C2 independently and by these functions F1 and F2. And the tampered code words are C1 star and C2 star. And then you have a decoder which decodes to M star. And then now we still need the similar function that M star is equal is epsilon close to function P F1 comma F2, and then some initial message and 1 minus P F1 comma F2, and the distribution df. Okay. Now, what do we mean by quantum secure? Okay. So what we mean by quantum secure in this paper is that you have the initial message M and the tampered code word is C1, C2, and then adversary is now more general. Adversary can potentially share the entanglement between the split code words and then try to tamper it to C1 star and C2 star. And this is what we mean by quantum secure non-malleable codes. Even when adversary is allowed to share entanglement and tamper the split code words, still we have this still we want to gain this requirement that tampered code word is somehow dependent on the adversary, and then 1 minus p adversary, and then the same distribution which depends only on the adversary. So this is what we want. And in this work, we do construct such quantum secure non-malleable codes in the split state model. Split state model. Okay. So how do we go about doing that? So we use the connection between quantum secure non-malleable codes and we use the connection between non-malleable codes in the split state model and two source non-malleable extractors. So both the non-malleable codes and non-malleable extractors seem like two different objects, but there is a very nice connection between both of them from the work of CG16, which explicitly gives the connection. So those who don't know what non-malleable extractors are, let me say a couple of sentences. Non-malleable extractors are a strong version of strong extractors, where non-malleable extractor output is uniform and independent, even given extractor output on a different seed, not just the initial seed for the seeded extractor, but also you are also given extractor output on a different seed. Okay, so now in this work, we extend this connection to ensure that we have, suppose if you have quantum secure non-malleable extractor, then we have quantum secure non-malleable codes in the split state model. So one can think of this work as quantizing this work of CG16, and then by using quantum secure two source non-malleable extractors, non-malleable extractors from recent work of Boddu, Jain, we get quantum secure non-malleable codes. Build codes in split state model. Okay. Yeah, so that's more or less that we do in this work. We also additionally construct efficient quantum secure non-malleable codes in the split state model by constructing efficient two source non-malleable extractors. What I mean by efficient here is that, suppose if I'm given the output of the non-malleable extractor, I should be able to sample from the pre-image of that output. Okay. So yeah, that's more or less about what we did in this work. Thank you, everyone.